What we're trying to get is as many of the pioneers in science and technology that we can get, and we would like to get from something that's not short, something between an hour and a half and 2 hours, if you could spare that long, or whatever you can spare. And we'd like to start out with some of your background, your personal background, and the education and what things led you into the field of science and that sort of thing. We've had some very interesting experiences, starting all the way from someone who had a physics notebook, that was C. Gray, which he filled out at the age of 7, and he had kept that. He showed it to us, all the way to Glenn Seaborg, who didn't decide to take any science courses until he was a junior in high school. So it varies all the way through. So, but if you can give you some of the background, and then we'd like to have you bring in some of the fundamental science for which you received all these awards, and we've had some very, very good ones from Ed McMillan and his opening up the transuranium, and Glenn Seaborg and his work and we've got some very interesting things. I thought I was up to date on a lot of that, but a lot of things were uncovered in that. So, for the most part, I will not do any interviewing, but I will, from time to time, I will ask you if you would expand or explain this and that sort of a thing. But for the most part, we'd like to just have an informal discussion with you, sort of a science autobiography.
Yeah, there's only one thing I want to say. I doubt if my voice will last more than about an hour.
Oh, well, that's fine. We'll just cut off whenever you wish to cut off.
Yeah, I just want to point that out. That I've had this. I caught it about 3 weeks ago, and I thought I'd be over it by now, but it's just hung on and hung on. That happens when you get older. But,
good. Well,
so I may have to beg off it.
Well, fine. That's perfectly okay. And incidentally, anytime you want to stop.
I brought some water in case I need it, and you can, if I pick it up, you can just cut that out.
Sure, that's right.
Or just leave it in, depending.
Just hold your finger up, and we'll stop.
I see.
We stop it, and it stops, and then you start right away.
Mrs. Larson can stop it if I do something like that.
Yep, that's
right. I see. Well, I may want to rest my.
Start again.
You don't even see it, so.
Right.
So what I do is I get about 60 seconds of introduction. Then I will say, "Please proceed, Dr. Fowler," and then you just speak naturally on that.
But you will make it clear that the autobiographical aspects are going to be stressed. Is that?
Well.
Because I thought I would start with where I was born and how I...
That's it.
Yeah, okay.
That's exactly.
Right. Mm-hmm. Very good.
All right. Jane, are you ready to push this?
It's already going.
Yeah. Mm-hmm. All right. And that's going to. So now. All right. Well, today, November 27th, 1985, we are privileged to interview Dr. William Fowler, whose many contributions to the field of physics was recognized by the Nobel Prize Award in 1983. To mention his many accomplishments and numerous awards would impinge on his valuable time. So with this brief introduction, please proceed, Dr. Fowler.
Well, Dr. Larson, I would like to begin with some autobiographical material. I was born in Pittsburgh, Pennsylvania, and although my family, my father's work was transferred to Lima, Ohio when I was 2 years old. Nonetheless, I'm still a Pittsburgh Pirate fan. The Pirates are a baseball club in the National League, and I'm still a Pittsburgh Steelers fan. The Steelers are a club in the American Football Conference of the National Football League. So, but on moving to Lima, it was a great change. Lima, Ohio was now and was then a rather small community. I think the population nowadays is something like 40,000 people. But it was a very interesting town. It was a railroad center.
How old were you when you moved to Lima?
Well, I was 2 years old.
Oh,
I was 2 years old. So my recollections of Pittsburgh come from the fact that all the grandparents were there and the uncles and aunts were there, and so every summer on my father's holidays we got on the train and went back to Pittsburgh. So I spent 2 weeks of every year during my youth in Pittsburgh, and with my grandparents and my uncles and aunts and cousins, and it was really something that influenced me greatly, because Pittsburgh was a big city, and Pittsburgh had a baseball team and it had a football team and so forth. But in Lima, it was surrounded by a farming community, but it was a railroad center. The main line of the old Pennsylvania Railroad from Chicago to Pittsburgh to New York went through Lima. The main line of the Erie, which went from Chicago to Pittsburgh to New York, went through Lima. The main line of the old railroad called the Nickel Plate from Cleveland down to St. Louis went through Lima, and a branch line, a very important one, of the Baltimore and Ohio from Cincinnati to Detroit went through Lima. So, and furthermore, Lima had a locomotive works. The Lima Locomotive Works built steam locomotives when I was a boy, and it continued to do so up until almost 1960. And in fact, my younger brother worked for the Lima Locomotive Works as a design engineer all of his professional life. So I was surrounded by steam, and in fact our home was only about half a mile from the big switching yards of the Pennsylvania Railroad just outside of Lima. And much against my father and mother's wishes, I spent a considerable period of my youth in the switch yards at Lima. And in those days, the rules weren't so strict, and the switch engine drivers would see this young fellow standing alongside the rails, and they would invite me up on the footplate, and they taught me how to drive a steam locomotive, which is not as simple as just handling a throttle and a brake. There's a thing called the Johnson bar, which determines when the steam is fed into the piston and so forth and so on. So I became fascinated with steam locomotives and have maintained that interest all my life.
How old were you when you drove your first locomotive?
Well, I must have been around, I would guess I was 6 or 7.
Oh,
I was 6 or 7. Oh, yeah.
I was going to say 16 or 17.
No, I was quite young, and in fact, if I'd been older, I doubt if the engine drivers would have paid any attention to me. But seeing this quite young fellow, you see, there's a fascination with steam which has carried over in my scientific career. A steam locomotive has a fascination because you can see how it operates. You can see the big wheels. You can see the big drivers. You can see the motion of the piston and all that sort of thing. In a modern diesel, you can't see anything, and it doesn't have nearly the fascination. So I think my interest in science and in engineering started with the steam locomotives of the Pennsylvania Railroad in Lima, Ohio. And that continued when I went to high school, although very soon it became clear to me that there was something different to engineering than driving a steam locomotive, and that there was something else beside engineering which my teachers called science. And in particular, my teachers in physics and in chemistry in high school had an enormous influence on me. Pop Edmonston, who was head of the physics department in Lima Central High School, and Cappy Sharman, who was head of the chemistry department, really got me started in my interest in science. However, when I went to Ohio State after graduating from Lima Central, I decided to go into engineering, and it was rather for a strange reason. I decided to go into ceramic engineering, of all things, although ceramics is a very important industry in Ohio. But I had written an essay sponsored by the American Chemical Society in those days for high school students on some subject in chemistry. Well, I wrote an essay on the production of Portland cement.
Oh, yeah.
And won third prize, which was $400, which was a lot of money in those days. That was 1929.
Very handsome prize.
So, and came in handy when I went off to college the next fall. So when I went to Ohio State, I enrolled in ceramic engineering, but very soon became acquainted with physics. And real physics, and in fact, all of the freshman engineers, as is common in many institutions, took the same courses, and it included physics, first-year physics for engineers, and mainly engineering laboratory, and mainly physics laboratory. Well, I was just fascinated by the physics laboratory, and that soon led to my decision to go into physics rather than into ceramic engineering, and this was made possible in part because just at that time the physics department at Ohio State under Alpheus Smith decided to establish a physics option in engineering. So they established engineering physics. And in fact, Leonard Schiff, who was quite well known in physics, his book on quantum mechanics is one of the books, and he was head of the physics department at Stanford before his death.
Well, that was quite early so far as engineering physics is concerned.
It was one of the first engineering physics courses in the country, and Leonard and I were two of the very few who opted to take engineering physics. And he was quite young then. See, we were freshmen at Ohio State when this happened. Leonard was a child prodigy. He was only 15. And so we got to know each other, and his family was quite wealthy. And his grandmother was very orthodox. And Leonard, and of course the family lived in Columbus. And Leonard would invite me to his home for dinner. And for the first time in my life, I had exotic Orthodox Jewish food when I'd been raised in a small, in a sense, country town in Lima. So it was just a revelation for me of how different life could be. And so Leonard and I remained good friends all during his lifetime. He went to MIT after graduating from Ohio State in engineering physics, and I went to Caltech. And then as postdocs, I stayed here as a postdoctoral fellow, and he came out to Berkeley as a postdoc under J. Robert Oppenheimer.
Oh, yeah.
Oppie, as we all called him. And I'll get to that a little later on. But at Ohio State, once I'd gotten into physics, I found that taking engineering physics was really up my alley, because in addition to taking physics courses, I took quite a few courses in engineering, especially in electronics and in electrical engineering. And I took laboratory courses in engineering, big electrical machinery. And I remember one of the professors, Johnny Byrne, permitted me to work in the brand new electronics laboratory that the electrical engineering department had just built. I remember he gave me the keys so I could work there on the weekends and at nights, and I remember spending a whole term studying the characteristics of a pentode, 5-electrode vacuum tube, which was the the thing in those days. When they were yay big. When I think now of how a little microchip can do everything they did, it's just incredible. But I learned a lot that way, you see.
Yes,
and I shouldn't stress it, perhaps, but it also meant that I didn't have to take courses in the humanities and the social sciences, which probably I should have done, but I emphasize it because it was in the engineering laboratories, which were, I must say, much more modern than the physics laboratories, that I really got some training in experimental physics that stood me in good stead when I came here to Caltech.
Yes, that's very interesting that you should mention your early training in engineering, because there are several other very prominent physicists like Wigner and Teller who had a very early training in chemical engineering. Went on, of course, theoretical physics from there.
Yes. Well, I must say that I think the fact that I was able to work in the electrical engineering laboratories at Ohio State as an undergraduate shaped more than anything else my decision when I came to Caltech to go into experimental physics, in contrast to theoretical physics. And in fact, I stayed in experimental physics for the first 30 years of my career. Finally, I got to the point where I felt that, I've got to stop grubbing away in the lab and start doing some thinking about what I've been doing all these 30 years. So, quite frankly, during the last 20 years, I've been to a certain extent a theoretical physicist in a rather limited sense in elementary particle physics. Certain theorists are called phenomenologists because they translate what's done in the high energy laboratory into the basis for doing high-powered physics on the experimental work. And that's been mainly what I've done in the last 20 years, is translate the work done in our laboratory and elsewhere on nuclear physics into essentially the rates at which nuclear processes take place in stars. But that's, again, getting ahead of the story. There was one other man at Ohio State, well, there were several people at Ohio State who influenced me quite a bit. Alpheus Smith, the head of the department, was very kind to me. He was a rather gruff man. He was called Bulldog Smith because of the heavy jowls that he had. And many people were scared to death of him, but I got to know him, and he gave me a lot of privileges of, again, working in the physics laboratories, kind of on my own. And in particular, he arranged for me to work with Willard Bennett, who was then a staff member of the physics department at Ohio State. And Willard Bennett was the first one to really introduce me to laboratory physics where you didn't know the answer. He was doing research himself, and he let me do an undergraduate thesis on magnetic focusing of electron beams. Well, that was just a whole new world for me, because in the electrical engineering labs, you essentially were doing things for which the answers were known. When I measured the characteristics of a pentode, there were textbooks you could go and read, which told you what the correct answer was, you see. Yeah. But Bennett put me to work on a problem for which the answer wasn't known, and of course that's the key to the fascination that all of us have in scientific research, that we can work on something where the answers aren't known and can find out something for ourselves. And so Bennett, I must say, Willard Bennett, got me started in that regard, and I've always felt a great debt to him.
Well, that's a very sophisticated experiment for an undergraduate.
Yes, it was, and I have to say that Bennett helped me a great deal. He built most of the equipment. There was some quite complicated glass blowing involved, and the tube in which we produced the electron beam was a long glass tube, which he had to blow and shape, and I built some of the things, and then I made the measurements, and he helped me, and so then he had spent some time, I think, as a National Research Fellow here at Caltech, and he strongly recommended that when I finished my undergraduate work at Ohio State that I go to Caltech. And in fact, I had always had some interest in coming to Caltech, and I had tried to come to Caltech as a transfer student during my junior year at Columbus, and but Caltech charged tuition.
Oh, yes.
And whereas Ohio State did not, because I was a resident of Ohio State, so I went to Ohio State free. We had to pay a laboratory fee of some small amount every year, but there was no tuition. Well, Caltech told me that I had to pay $300 a year.
Yes.
Well, that was a lot of money, as I've said before, in those days. So
that is inflated slightly now.
Yes, it certainly is, by over a factor of 10. But and I had been attracted by Caltech because in 1921 Millikan had become the head of Caltech, and everybody knew about Millikan in those days. In fact, our high school textbook that Pop Edmondson used in his physics course was written by Millikan, and I don't think it was Millikan and Gale, but it was one of the books that Millikan and his collaborators wrote for high school physics. So we all knew Millikan. He was the first. He was the first native-born Nobel Prize winner. Michelson had won it previously, but Michelson was born in Europe, and so Millikan was very famous, and because he went to Caltech, that made Caltech rather famous too. So, to make a long story short, I applied for a graduate fellowship at Caltech, and to my great joy, I received a telegram from the great man himself, from Robert A. Millikan, saying that yes, indeed, I was admitted to the graduate school, and I had a graduate fellowship which would provide me with room, board, and tuition, but no cash. So I had to scramble to raise enough money to pay for the train ride to California, and it was pretty tough because my father, who had left school at 13, was bound and declared that his children go to college, and he had helped me insofar as he could in my undergraduate work at Ohio State, although I had to do quite a bit of work on my own. I served meals and washed dishes for the Phi Sigma Sigma sorority and stoked the furnace in the wintertime, and I worked at the Central Market in Columbus on Saturdays, starting late Friday night and all day Saturday to make some money. So, but my father helped me insofar as he could. But when I went to him at my graduation from Ohio State, he expected me to come home, get a job in Lima, and help put my younger brother and younger sister through college.
Oh, yeah.
Well, when I told him I was going to go to graduate school, he just about fainted. He had never heard of graduate school.
Yes, that's right.
And I can sympathize with him. He thought, oh, this boy's goofing off, and instead of coming now and helping, he's going off to California and leaving the rest of us in the lurch. But he finally realized, and he helped me again as much as he could, and in fact, he got me a job that summer before I came out to Caltech after graduation from Ohio State. Got me a job in the local YMCA where I made some money to pay for my train fare. So it all worked out. And I got out here to Caltech, where I've been ever since. Came here in '33, so as a graduate student, I've now been here 52 years, and around the campus I'm known as the oldest graduate student.
Well, that's very interesting.
Which,
yeah, that was about the time that Dr. Towns came to Caltech.
Well, Charlie came somewhat later. Charlie was a graduate student when I was a postdoc from 1936 to 1939.
Oh, yes.
I got my PhD between 33 and 36, and Charlie did his work between 36 and 39.
Oh, yes.
But I knew him very well, and in fact, Charlie played a rather important role in my own research because, and I might get to that later on, the role that Charlie played. But I came to Caltech in 1933, determined to go into some kind of experimental physics, and in fact, I had a predilection to go into the photoelectric effect because Millikan had measured the value of Planck's constant that way. And but I got out here and found that most of the excitement had to do with experimental work in nuclear physics. Now, as you will remember yourself, 1932 is considered the great year in nuclear physics. In 1932, Harold Urey discovered deuterium. Carl Anderson discovered the positron. Chadwick discovered the neutron. And Cockcroft and Walton showed that you could disintegrate nuclei by accelerating particles to energies of the order of 1,000,000 volts or so, or even less. Well, Charlie,
and of course, at that time, I believe Lawrence worked with the cyclotron that same time.
That's right. So Lawrence started work with the cyclotron, and the man I went to work for, and the man who had the greatest influence on my life, was Charles Christian Lauritsen, who was here who had been here since the middle 1920s. In fact, Lauritsen built this laboratory, the W.K. Kellogg Radiation Laboratory. He designed it and built it, and it was finished in 1931, just 2 years before I came. So I have worked in this laboratory essentially since its foundation, but it was Lauritsen who had the dream and who built the lab. And it was Millikan who got the money from the Cornflakes King, W.K. Kellogg, Keith Kellogg, to pay for the construction of the laboratory.
Is that the same Lauritsen who developed the Lauritsen electroscope?
Yes, yes. Charlie devised the Lauritsen electroscope as a very sensitive detector, given its simplicity. For all types of radiation, gamma rays and neutrons in particular. And when I think back on how simple the Lorentz electroscope is. I've got one right here.
Oh, yeah.
You want to hand me that, Mrs. Larson? Yeah, just.
Yes,
there,
well,
just as long as we're
now,
talking about.
I purchased one of those and I'm doing work in 1937 or 8, and I think we paid $60 or something like that.
Well, here's the chamber in which the radiation produces ionization, and there's a very small quartz fiber
the gold
mounting in there, gold-plated quartz. And then you look through this eyepiece and held it up to the light, and you can see the little fiber. It's still there after all these years.
Oh, yeah.
And that was the instrument that we used for much of the detection of the radiation produced in nuclear reactions in the early days.
Oh, as a matter of fact, Glenn Seaborg did a lot of his early work with the Lorentz electroscope,
and right. So, well, Charlie was an incredible person. He was not only a physicist, he was an engineer. He was a radio engineer for some years. He was an architect before he came to the United States from Denmark. And he was also an accomplished musician. And I remember in those days, he had a Friday night seminar for all of his graduate students. And after the seminar, we would go to his home to drink beer and to sing. His son, Tommy Lauritsen, who later on joined us, Tommy was an undergraduate in those days. Tommy played the piano and Charlie played the violin. And all the graduate students had to sing. And mainly what we sung was Carl Michael Bellman. Carl Michael Bellman was a very famous poet and musician of the 17th century Sweden. And he wrote a great number of songs, and as is well known, most of the songs were drinking songs. Well, that made it all that much the better, as long as we were drinking beer. So we had to learn Carl Michael Bellman. He was Swedish, but Charlie, being Danish, knew about his work. And I must say, one of the most enjoyable parts of my visit to Stockholm a couple of years ago was the fact that I was able to sing along with the Swedish students, sing Bellman with them. And they were just fascinated that that someone from Lima, Ohio, could sing. At least knew some of the words of Bellman's drinking songs. So Charlie had an enormous influence on my life, and he guided my graduate research. And at the same time, Robert Oppenheimer played a significant role. Charlie and I were doing research in what was then this new science of nuclear physics. When Charlie found out that Cockcroft and Walton could disintegrate nuclei with energies with an accelerator with energies less than 1 million volts, just like Ernie Lawrence, he changed one of his X-ray tubes into a positive ion accelerator and started doing nuclear physics. He had built the X-ray tubes because he wanted to do X-ray physics and cancer therapy, and Mr. Kellogg supported the research because of the cancer therapy. And in fact, that lasted the research in X-rays and in cancer therapy lasted up to the war at the same time, simultaneously with the new work in nuclear physics. So, in fact, I got my fellowship by helping maintain the X-ray tube, which was located in this building. And on this floor we're on now, the doctors who carried out the research in cancer therapy were all located here. And we graduate students who had fellowships kept the 1 million volt X-ray tube running, so that in the mornings the doctors could treat cancer patients. And then in the afternoon, the tube was free for some of Charlie's graduate students who were still working in X-ray physics. But I went into nuclear physics with Charlie, and my thesis was on radioactive elements of low atomic number. We studied the positron decay of radioactive nuclei like carbon-11, nitrogen-13, oxygen-15, fluorine-17. And this is where Robert Oppenheimer comes in. He had a joint appointment in those days between Berkeley and Caltech. In those days, Berkeley started very early in the fall, sometime in August, and then their term finished early in the spring. So he was able to come down after school had finished in Berkeley to Caltech for our spring quarter. And so he would do that. And doing that, he essentially was the theoretical advisor for my PhD research. Well, Charlie and I found that the beta decay energy of this series of radioactive nuclei increased quite uniformly. And in fact, that this energy was just comparable to the Coulomb energies or to the electrostatic energies in these positively charged nuclei. Carbon-11 has charge 6, nitrogen-13 charge 7, oxygen-15 charge 8, fluorine-17 charge 9, and these energies increased uniformly. And it was Robert who pointed out to us that this was just the electrostatic energy, which was the difference between the so-called mirror nuclei. Carbon-11 goes to boron-11 and so forth. And, well, to make a long story short, he pointed out that this meant that the nuclear forces were charged symmetric. You had to have the same force between two protons as between two neutrons if you exclude the fact that the protons are charged and also have an electrostatic energy. Take that away, the forces were the same. So we discovered something fairly fundamental about nuclear force, but I can say we would never have known what it meant if Robert hadn't been on the ball and knew what was going on, you see. And in fact, that was fairly characteristic of the situation in those days. Charlie was a great man. He had a deep knowledge of physics, but he was primarily an experimentalist. And so for him, the fact that Oppenheimer could come down during the spring quarters meant that his students could get some theoretical advice, and as well as grubbing in the lab during the rest of the year. So it was a great thing. And another man who played an important role was Richard Tolman, who was professor of chemistry then, but was essentially a physicist, I say. And Tolman and Lauritsen and Oppenheimer were very, very close, very, very close. And I can remember when I was working as a graduate student with Charlie, quite frequently Robert and Richard Tolman would pop into the lab and sit down and just watch while we were working, and Charlie would let me take the readings, and I'll never forget the discussions they had, ranging from everything to the coming World War and to basic problems in physics. So, and then I must go back to mention the role that Charlie Towns played. Shortly after I finished my thesis on these radioactive nuclei of low atomic number, Lauritsen and I decided to study the interactions of the isotopes of carbon and nitrogen with protons. And one of the isotopes of carbon is a rare one, carbon-13. I mean, normal carbon, or most carbon, is carbon-12. It's 99%. Carbon-13 is the heavier isotope. They both have charge 6, but the heavier isotope is only about 1%, so it's very rare. And if you just take an ordinary target of carbon and try to see what comes from the carbon-13, it's swamped by what comes from the more abundant carbon-12. Well, Charlie Towns was working for Ralph Smythe then as a graduate student, Professor Smythe, who was in mass spectroscopy, and one of the things he was doing was separating the isotopes of the light elements. So when I wanted to bombard carbon-13 with protons and to study what happened, I went to Charlie Towns, and Charlie supplied me with enriched samples, which he was producing as part of his thesis research under Professor Smythe. So Charlie Towns helped with my postdoctoral research. And that, of course, culminated. Charlie and I were bombarding carbon-12 and carbon-13 and nitrogen-14 and nitrogen-15 with protons. And all of a sudden, in 1939, Hans Bethe announced that the interactions of protons with those isotopes constituted the carbon-nitrogen cycle by which energy is generated in many stars. Well, that was just an awakening. I've been hooked ever since. We suddenly realized that what we were doing in the laboratory was studying processes that occurred in stars and generating the energy with which stars shine. And so, as I said, I was hooked. Charlie was hooked, and we decided to concentrate on the aspects of nuclear physics which have to do with energy generation in stars. We came eventually to call this field nuclear astrophysics. I emphasize that it's a benign application of nuclear physics. As we all know, there are many applications of nuclear physics that are not so benign. But it's always been a kind of paradoxical situation for me, but I tend to look on the sunny side of things, and in this case, I use the word sunny rather literally.
Yes, that's right.
Because the sun shines by these, not by the carbon-nitrogen cycle, but by other processes, which Hans Bethe also suggested. It's called the proton-proton chain, and we needn't go into the details. Well, the war came along just about that time, and eventually this laboratory was transformed into a center for the development of rocket ordnance. We essentially built small rockets, primarily for the United States Navy, and we helped the Navy establish the Naval Ordnance Test Station at China Lake. And in fact, toward the end of the war, when it became clear that the atomic bomb was going to work after the Trinity test, well, even before Trinity, we transferred all the rocket ordnance work to the Navy and began doing producing non-nuclear components of the atomic bombs for Los Alamos. And Charlie and I, mainly because of our connection with Robert Oppenheimer, who was the director of Los Alamos, we began to spend a great deal of time at Los Alamos at the same time that we were phasing out the rocket work, finding out what we could do to help with the work at Los Alamos. For example, for the plutonium weapon, it's housed in an enormous bomb casing.
Let's see, I believe they call it Fat Boy.
The Fat Boy, but the ballistics, that is the trajectory that such a bomb would take when it's launched from an airplane, just wasn't known at all. And so a great number of dummy bomb casings, which we call pumpkins, had to be built. We built hundreds of them. And they had cement put inside to put the center of gravity in the same place. And then we would modify the tail structure according to what Los Alamos wanted. And we would take these up to Wendover, Utah, where the Air Force had a B-52 test range. Or was it B-32s? It must have been, And I remember going up there. They'd drop these things until they learned what the ballistics were going to be, and so that's the sort of thing that we did. Well, finally the war ended, and fortunately successfully,
Yeah.
but with consequences that remain until the present time. That's again a great problem for all of us who took part. I'm sure you know as well as I do. We felt we had to do what we did, but there are always lingering doubts about whether the development of atomic weapons was the right way to go. I personally think it was, but I can see why many people feel that perhaps there were alternatives that might have succeeded. My own recollection is at the time we were convinced it had to be done. We were scared to death of Hitler and the Germans. We were scared to death of the Japanese, and so it happened, and we have to live with it. But finally, the war ended, and Charlie and I, and Tommy Lauritsen, his son, who had done his PhD just before the war under his father, just as I had, although I worked with Tommy a great deal on his graduate. He joined the faculty after the war, and so we set about getting rid of all the defense work and reestablishing Kellogg as a nuclear laboratory. But we made a quite different decision than Ernie Lawrence made. Not to say that what we did was right or wrong. I think both decisions have worked out quite well. Ernie decided to go into higher and higher energy nuclear physics, which has resulted, as you well know, in things like the Fermi Lab, where the energies are in the billions of volt range and now going to be in the teravolt range, and CERN laboratory in Geneva. But the Lauritsens and I decided to stay in low energy nuclear physics because that's where the applications in astronomy, in astrophysics, occur. And so we, to a certain extent, contrary to the way most other people were going, we developed we developed low voltage electrostatic accelerators, following most closely the work of Ray Herb, the pressurized electrostatic accelerator, which was an improvement that Herb of Wisconsin made over the original designs, the open air designs of Van de Graaff. So we followed Herb's direction and worked for very high resolution in the energy of the beams produced by our electrostatic accelerators, and very high energy resolution and very high sensitivity, more or less, in the detection schemes.
Oh yes. Let's see. I think the Van de Graaff, of course, has a tremendous value because of its precision and control of the energies.
Yes. Well, you see, we realized that that's the way we had to go. Yeah. When I think back on it now, the accelerator that I used was powered by alternating voltage, because with alternating, what Lauritsen used for his power was power from the alternating current transformers that Royal Sorensen, the head of electrical engineering here, had built to test the towers and the transmission lines for the Hoover Dam power system, you see. So when Charlie changed from producing X-rays with alternating voltage, he made his tubes into positive ion accelerators, and that meant that you had a beam which had all the energies from 0 up to the maximum. Now, actually, the focusing was such that the beam was mostly at the higher energies, but it had a resolution maybe of 20 or 30%, not of the tenths of a percent, which you can get from a Herb type Van de Graaff accelerator. So we built our own. Tommy Lauritsen and I built the first one, and actually we built it before the war in 1938 and 39. But then, as I said, the war came along, and it was moved into a corner. And then after the war, we had to put it back into operation. We built a still lower. That machine, as I remember, had a maximum voltage of about 1.8 million volts. Then we built another one for still lower energies and higher currents, and still higher resolution, that operated up to about 700 kilovolts. And then we built a still larger one that operated to 3.5 million volts. So with those three machines, we were able to maintain a fairly extensive program, partly in pure nuclear physics, but primarily devoted to studying those nuclear processes which the theorists told us occurred in stars.
Oh, yes. And today, of course, your tools there, you had rather high currents available too,
yes,
so that you could study.
Yes, because
it's a very important thing.
As you know, as you go to lower energies in bombardment, the probability of the nuclear reactions gets smaller and smaller. And that's due to the fact that the interacting nuclei, the protons, which are the nuclei of hydrogen, and say the carbon-12 nuclei, they're both positively charged. So, I mean, like charges repel. So you have to give the proton quite a bit of energy to get into the carbon nucleus, where it can fuse and then break up. In that case, into the emission of a gamma radiation, with a transition to the ground state of the carbon-12 or carbon-13 nucleus. So we had to, and although in classical mechanics this can't even happen, in quantum mechanics there is a penetration permitted through what's called the Coulomb or electrostatic barrier. But as you go to lower energy, the probability of that penetration gets smaller and smaller. In fact, it's an exponential decrease. So you're quite right. We had to have higher and higher currents at lower and lower energies, and that's what we concentrated on. And you can't design one machine to cover the full range of energies, and that's why we had three of them. And eventually, in 1960, to jump ahead of the game a bit, we obtained a tandem electrostatic accelerator from the High Voltage Corporation, the first one that we didn't build on our own, which operated up to about 7 million volts on the terminal. It is still in operation over in the Sloan Laboratory, adjacent to the Kellogg Laboratory here. And then just a few years ago, we found that all of our old equipment that we had built was just becoming obsolete and was costing more to maintain than was worth it. So we got a 3.5 million volt machine, tandem, from Ray Herb's outfit in Wisconsin, the second one that we hadn't built. And it's our workhorse now because it delivers very high currents down to very low voltages with extremely high resolution. And see, along with the advantages of the Van de Graaff accelerator, as you pointed out, in producing high resolution beams, you have to go beyond that. You have to have big magnetic analyzers to put the beam through so that you can further improve the resolution. And by a feedback mechanism, if the beam going through the magnet with its proper setting begins to move off, feedback tells the accelerator to correct that. Then in addition, you have to have very thin targets. You have to have very sensitive detectors. And of course, right after the war and up to the present time, the detectors have been complicated electronic devices, sodium iodide crystals with phototubes looking at them, and it's a far cry from what what we did before the war. But
fascinating things they can do with those.
Yes, yes. Well, much as I love this marvelous little gadget, I have to admit that it's been the development in electronics, and especially what's been done in recent years with the microchips that has made possible what we're doing in the lab, and we've tried to stay abreast of that, and in fact, I think we have one of the best equipped labs in that regard in the country, although we operate at a considerably smaller scale than the big laboratories like the one that Ernie Lawrence built at Berkeley, which has grown up into the Fermi Lab, and SLAC at Stanford, and CERN at Geneva. But we have a staff of 5 full professors and quite a few postdoctoral students, quite a few graduate students, and quite a few postdoctoral fellows. So we have an operation that involves about 50 people, and we're still primarily concerned with studying those processes, those nuclear processes, which we think take place in stars. Going back after the war, we did get into the study of the carbon-nitrogen cycle, which we had been working on before the war, and learned from Beta that it was important in stars. We improved our measurements, and we went on to do other things that were directed toward problems in nuclear astrophysics. One of the very popular theories after the war was that due to George Gamow, which suggested that all of the elements had been produced in the early high-temperature, high-density stage of the universe, which we call the Big Bang. Even before the war, Hans Staub and William Stevens here in Kellogg had confirmed the fact that there's a mass gap in the periodic table at mass 5. There's no stable mass at mass 5, where by 5 we mean a mass that's roughly 5 times the mass of the proton, the mass of the lightest, the nucleus of the lightest element, hydrogen. So they had confirmed that there was no stable nucleus at mass 5.
See, there are radioactive?
Yes, there are 2 radioactive nuclei. There are nuclei of helium-5, and of the element lithium-5. They both break up in a microsecond.
Yes.
So as fast as you make them, they are just destroyed. And Staub and Stevens had shown that, as well as other people. Then after the war, Alvin Tollestrup, who was one of our early graduate students after the war, Lauritsen and I, showed that the same thing happened at mass 8. There, the nucleus, if it is stable, would be an isotope of beryllium, beryllium-8. Well, the geochemists had long suspected that beryllium-8 was not stable, because the form that you find beryllium in nature is beryllium-9, which is stable. So then, after the war, there was some work done in nuclear laboratories which suggested that the beryllium-8 was stable. So we looked at we produced beryllium-8 and found out it always broke up into 2 helium nuclei of mass 4. As fast as you made it, it again broke up. 1,000th of a microsecond is the lifetime. So there's a gap at 5 and 8, and Gamow's theory was that all of the elements and their isotopes had been made by neutron capture with the emission of gamma radiation. Well, the neutron also has roughly a mass of 1. So you see, with neutrons, you have to have every number. You start with hydrogen, you go to deuterium, you go to helium-3, you go to helium-4. When you go to 5, break right back down to a neutron plus helium-4. And even if somehow you get around that gap, by the time you get to H, you've got another one. You make mass 8, it breaks right back down to 2 helium nuclei and mass 4. So we played a role in this laboratory in the it took some time to convince him, in convincing Gamow that his scheme wouldn't work beyond mass 4.
So in 60 billion years, there's not enough time for those 4s to. Well, suppose you have for a billionth of a second, you have an isotope which has 5. Presumably, it could that 5 could capture another one and go up. But then, by the time it got to 8, you would.
Well, you're certainly on very close to the ultimate solution, which again turned out to involve stars. In the Big Bang scenario, the hope after the fact was discovered that there was no mass 5 and no mass 8 was that you could put 2 helium-4 nuclei together in the first instant of the universe, the so-called Big Bang. Put them together, have them stick together long enough that another helium-4 hit them. That would make carbon-12. 3 times 4 is 12. You make mass 8 out of 2 helium-4. Or alpha particles, as Lord Rutherford called it. Then they do stick together, and if the density and temperature are high enough, then another helium-4 can hit them while they stick together, and that'll form carbon-12 for you. Well, that won't work in the Big Bang, because in the Big Bang, after the helium-4 is made, the Big Bang is in the expanding universe. When something's expanding, the temperature and density are dropping. So that after the helium-4 was made, you didn't have the temperature and the density continued to drop. So you didn't have enough collisions of helium-4, the density was so low, to form the carbon-12. But it was Edwin Salpeter at Cornell who first suggested, on the other hand, this process could occur in red giant stars, where, quite contrary to what happens in the Big Bang, in a star, after it's gone through what we call the main sequence stage, where it essentially converts hydrogen into helium by nuclear processes and gives off, the energy with which a main sequence star shines. After it's converted all the hydrogen in its central regions into helium, gravity, the internal gravity of the star, takes over. It's not expanding like the universe. The gravity takes over and compresses the central region, raises the density and raises the temperature to the point where Salpeter pointed out this helium fusion, 3 of them into carbon-12, which is stable, but could occur. Well, in fact, that came about because when Salpeter came here in 1951, he found out that Tollestrup and Lauritsen and I had shown that the beryllium-8 was only unstable by something like 90 kilo electron volt. I think we got 85. Now it's known to be very close, 90 with a bunch of significant figures after the decimal point. Anyhow, when Salpeter found out that the beryllium-8 was only unstable by 90 kilovolts, he realized that it would stick together. Would be populated in the center of the red giant stars, and the ones that lived for a short time would be hit by another helium, because the density in a red giant star is enormous, something like 100,000 times the density of water, and the temperatures are billions of degrees, or, well, at least 100 million degrees. So in red giants, it ought to occur, and that's where Fred Hoyle comes in. As you know, I've worked ever since 1953 with Fred Hoyle, and I must say right at the outset that the grand scenario of element formation in stars, just like is due to Fred Hoyle, just like the grand scenario of energy generation in stars is due to Hans Bethe. Well, Hoyle took saltpeter's suggestion quite seriously and worked on exactly how this fusion of helium, you see, this jumps the gap to 5 and 8. You go directly to 12, just like you surmised. And Hoyle started looking into that, and he was a theoretical astrophysicist working on stellar structure, and he came to the conclusion that when he compared his theoretical calculations on red giant stars with the observational material on red giant stars, what the astronomers found out about them, that the red giant stars had to ignite the helium fusion into carbon at a lower temperature than saltpeter's theory gave. So Hoyle modified theory, and he did it by saying that when the beryllium 8's sitting there and is going to interact with another helium coming up toward it, there's a resonance in that process. A resonance, just like when you start pushing a swing, you can get just by going at the right frequency, you can keep the swing, you can get the swing going into greater and greater amplitude. So Hoyle suggested that there was a resonance in this process which would enhance the rate beyond what saltpeter had calculated without the resonance. Now, I know that's highly technical, but Hoyle immediately realized that a resonance in this process required that there be what we call an excited state in the carbon-12 nucleus at an energy that he could calculate fairly precisely just from the astrophysics. He calculated it as something like 7.558 million electron volts, and he was just convinced that this excited state had to be there. Well, there had been some observations even before the war that maybe there was such an excited state, but after the war, improved work at MIT had looked for this excited state, and they hadn't found it. So Tommy Lauritsen, who kept the books on all excited states, had erased it. And so when Hoyle came to the lab in '53 and talked to us about this, Lauritsen, the two Lauritsens, and I told him to go away. There was no state there. I mean, we were busy, and stopped bothering us. But fortunately, Professor Ward Whaling in the laboratory listened to Hoyle, and he and his group, postdocs and graduate students, went in the lab to find this state in carbon, and by golly, they found it to be almost exactly where Hoyle said it was. They got 7.56 instead of 7.58.
That's amazing.
Well, that, I must say, made a believer out of me. You see, Bethe had gotten us fascinated with energy generation in stars. Hoyle was producing elements in stars, so there was a new reason for working in nuclear astrophysics. That was all in '53. Charlie and Tommy and I immediately jumped into the problem after Whaling had shown that this state exists. We, along with a graduate student, showed that the state could be formed by putting 3 helium nuclei together. It has to have special properties. It has to have the correct spin and parity, we say in our terminology, and we found out that it had the proper combination of spin and parity, that it could be put together. So then I got a Fulbright to go to England to learn more from Fred Hoyle in 1954, it was there that Fred introduced me to Jeff Burbage and Margaret Burbage, and then in '55, the Burbages came back here to Kellogg with me. Well, actually, Jeff got a Carnegie Fellowship at the Mount Wilson Observatory. Margaret had a postdoctoral fellowship here in Kellogg. And one thing led to another, primarily some work that Hans Suess and Harold Urey did, which unraveled many of the complexities, the apparent complexities in the abundances of the elements and their isotopes. Once we were aware of what Suess and Urey had done, then we came forward with a general theory along the lines of Hoyle's grand scenario, in which we proposed nuclear processes which could produce all of the elements all the way up the periodic table to the radioactive elements, thorium and uranium. And I must say that at the same time, this was 1957. This was independently done by Al Cameron, A.G.W. Cameron, who was then at the Chalk River in Canada. He's now a professor of astrophysics at Harvard. But I think it's very important to know that Cameron independently did what the Burbages and I did. And I've always, when I look back on how furiously the four of us had to work on all these problems after we got an inkling of how to go from Suess and Urey, when I think back of how hard we had to work and realize that Cameron did essentially the same thing single-handedly. It's just fascinating. And while I'm passing out credits, I think it's very important for me to stress that the award to me several years ago, I look on as an award to this laboratory, to the memory of Charlie and Tommy Lauritsen, and to my colleagues here who really have done most of the experimental work over the years. I've already mentioned Ward Whaling, but in addition, Charles Barnes and Ralph Cavanaugh, both full professors, and now Brad Philippone, who's an assistant, new, young, vigorous assistant professor, are carrying on the experimental work. And the theoretical work, which had started with Oppenheimer, was in the early days carried on by Bob Christie, who is now Professor Emeritus of Theoretical Physics at Caltech, and then at the present time by Professor Steve Koonin here in Kellogg. And I have to emphasize that if it hadn't been for the work of so many people, all those staff members I've mentioned, legions of graduate students and postdocs, that the field of nuclear astrophysics could not possibly have been recognized in the way it was.
Of course, this whole field involving the development of the isotopes through the periodic table, that has given us so much of a more of a comprehensive picture of the nature of our universe. That,
yes, I think
as a matter of fact, it always surprises me that this much knowledge has come out from such a small group. Yourself and the rest of your colleagues have done so much in that.
Well, I have to emphasize, too, that it's true. I mean, our laboratory has been a leader in the field, but there have been many other laboratories have contributed all around the world. And it's a very active field, both experimentally and theoretically and other places. And it's still extremely exciting. Philippone and Barnes are studying the next process that occurs in red giant stars after the carbon is produced. You start with the 3 heliums, making the carbon-12. Then the carbon-12 can be hit by another helium-4. When they fuse together, that makes oxygen, the main isotope of oxygen, oxygen-16, 12 and 4, 16. Well, the ratio, mind you, of the rate of that process, which they can measure down in the laboratory, to the rate of which the 3 heliums fuse to make carbon-12, the ratio of those 2 rates determines the ratio of how much carbon to oxygen is made in red giant stars. And that's where we think our carbon and oxygen are made. That's important to us because we're mostly carbon and oxygen. We're, I forget, 65% oxygen, 18% carbon, and we're still about 10% of the primordial hydrogen in the water in us. That's right. But the carbon and oxygen are important to us, and that's because they're made in stars. I sometimes tell my audiences that we're all made literally and truly just a little bit of stardust, and we think we know the rate at which the fusion of helium, thanks to Hoyle and Whaling, into carbon occurs, but the fusion of the carbon with another helium to make oxygen it's a very difficult experiment. You have to go to very low energies. The probabilities are very low, and the setup is just incredible, incredibly complicated, but Filippo and Barnes and the graduate students and the postdocs are working hard at it. When they get the right answer, then we'll do as we do with everything else, translate their results into the rates under astrophysical conditions, and then the theoretical types who work on what happens in a red giant star, and when it eventually becomes, say, a supernovae or a novae, they can then calculate how much carbon and oxygen are produced. Now, we know that in our solar system, the oxygen to carbon is about 2 to 1. Well, the preliminary results we get when we kind of leak them to our friends and they make some calculations, doesn't come out right. So, but that's what makes it fun. That's what makes it fun. There's a problem. And when the boys finally get the best answer they can get, then the theorists are going to have to live with it. And because you see, they put the nuclear reaction rates in. We try to give them the best data possible, and other laboratories do, so the nuclear physics, uncertainties in the nuclear physics, don't complicate the problem. Then they, in turn, can adjust the internal structure of a star, which means adjusting the density and the temperature, to find out under what conditions the process works given the nuclear reaction rates and a lot of other atomic physics opacities. So it's a fascinating game.
It's a fascinating
and
thing.
it's still an exciting game, in spite of the fact that it's 50 years old now, and as many people say, it's a mature science. Well, I say to hell with that. I mean, I'm not mature.
There's still a lot of things to be unraveled here. Now let's see. This shows my ignorance in the field, but let's see. This all over what span of years did the synthesis of carbon? It's such a difficult process. And the probabilities are so small. How long did this take?
Well,
billion years, or is it very fast? Or
yes. Well, it turns out that because in the synthesis of the elements in stars, when you get way up to the end of the periodic table, these processes produce the radioactive elements, uranium and thorium. And radioactive elements serve as chronometers. The geologist uses the decay of uranium and thorium to date the age of a rock. Now, we can do the same thing in this sense. When the elements are being produced in stars, the stable ones last. The radioactive ones begin to decay, and that decreases the final amount that you get, because because as fast as they're being produced, a few decay. Now, the lifetimes of the thorium's has a half-life of about 13 billion years.
Mm-hmm.
One of the isotopes of uranium, the heavy one, has a half-life of 4.5 billion years. The lighter one is around a billion years. So they're excellent clocks.
Mm-hmm.
And using the same principle, it's essentially the idea of the hourglass. You can think of the parent that's going to decay as the sand in the top of the hourglass, and the daughter after the decay as the sand in the bottom, and that the radioactive decay is similar to the sand going through the neck of the hourglass, you see. So that's the way in which there are clocks, and so by writing down the appropriate mathematical equations, we can use our ideas of the production of the radioactive nuclei, and there are lots of them, but mainly uranium and thorium, to tell us how long it has taken to make the elements in the galaxy, in stars in the galaxy. See, I have to emphasize that the chemical elements in our bodies, in the Earth, in the planets, in the sun, were produced in stars in our galaxy, which we call the Milky Way, were produced before the solar system formed. Now, we know that element synthesis is still going on, but we're not getting any contribution from that. The sun formed, we know, 4.5 billion years ago, almost exactly, out of a solar nebula that condensed under gravitational forces, the details of which we are not even sure about. But we know that it happened 4.5 billion years ago. But that solar nebula consisted of hydrogen and helium from the Big Bang, which was about 15 billion years ago, plus the heavy elements made in stars ever since our galaxy, the Milky Way, had formed. Each star has to generate energy. It converts light elements into heavy elements. It eventually puts its nuclear ashes back into the interstellar medium. And then when a new star forms, like our sun did 4.5 billion years ago, it inherits the nuclear debris of the nuclear processes that occurred in previous generations of stars. So we can tell how long that occurred, and that gives us then the duration of nuclear synthesis before the formation of the solar system. I think that's something like 6.5 billion years. You add the 4.5, that gives 11. Then you add 1 or 2 billion years for our galaxy, the Milky Way, to form after the Big Bang, and so you get 13 billion years. I gave 15 back to the formation of the universe, and so we're involved in that aspect of cosmology. It's a very exciting one at the present time, and so we're still having fun. But one of the things we can say is how old the elements in your body are. And then you asked me about a particular one. If we could have the time, we could tell. We can say in some ways where it was produced and when it was produced, and so forth and so on. So that aspect is very exciting. I want to emphasize in conclusion that the field is still a very active one. The one of the most promising lines of endeavor is that in stars, the excited states of nuclei are populated, as we've talked about. Radioactive nuclei, even though they don't live very long, are involved in stars. Well, most of the radioactive nuclei don't live long enough that we can get enough of them to bombard in the laboratory. So the new scheme is to turn the thing around, produce radioactive nuclei with a big accelerator, like the Triumph facility in Vancouver, Canada, produce them by bombarding with very high energy protons, 500 million electron volts, bombarding stable targets. That produces scads of radioactive nuclei. picking those up, focusing them through an online isotope separator, it's called, and then putting them into a post-accelerator and using the radioactive nucleus as the projectile and let it hit a target of gaseous hydrogen, for example. The radioactive nucleus hitting the hydrogen is exactly the same as the hydrogen hitting the radioactive nucleus, but it's just relative velocities is involved. So we're all excited about the possibilities of producing radioactive targets, radioactive nuclei, and what we call isomeric states, excited states, the relatively long-lived ones of stable nuclei, and studying their properties, because when we make detailed comparisons of what we're finding in the laboratory and what the theorists calculate, we find that the big problem is we don't know the reaction rates for these radioactive nuclei and the isomeric states or excited states of nuclei. So that's a whole new field that is opening up, and I think it's going to be the most exciting development in nuclear astrophysics in the next decade. And my colleagues and I here in Kellogg are working very actively with a group in Canada at the Triumph facility in Vancouver to push for the construction of an online isotope separator in connection with the Triumph facility, and then a post-accelerator to do nuclear astrophysics. So there's some hope that we'll reach a solution of the many problems of why we have as much carbon, why we have as much oxygen, why we have as much potassium, why we have as much calcium in our bodies.
That's fascinating, fascinating subject, and as you say, there's still a lot to be unraveled in this whole thing. But it's so important to the understanding of our universe, and that.
Well, I think knowing where the chemical elements come from is something that appeals to all of us. We like to know our origins, and the fact that we're all stardust in the sense that what's in us was beyond helium, was made in stars. I didn't say anything about the three rare elements, lithium, beryllium, and boron. I've worked on that with Hoyle in another connection. And with a man named Hubert Reeves, we think that lithium, beryllium, and boron are produced by a quite different process. Namely, they're produced in the interstellar medium by the cosmic rays bombarding the still heavier elements, the carbon and the oxygen and the iron and so forth, in the interstellar medium that had been produced in stars. And the cosmic rays hit those, they fragment them and make these light elements 3, 4, and 5, lithium, beryllium, and boron. So,
yes. Because again, there's a very elementary question. If I could ask you one more on with regard to the lighter elements, there are a few naturally radioactive ones, like potassium, for instance, and I guess there's a couple other examples. But if you let's see, why ordinarily you think of the heavy ones are the ones that would be unstable and naturally radioactive, but why is it that potassium is, you might say, radioactive and hasn't disappeared or so forth?
Yeah, well, the form of potassium that's radioactive is the isotope that has mass 40, and it can decay into argon 40, which is stable, or into calcium 40, which is stable. Now, it turns out, as I remember,